Carbon and its compounds. Food, clothes, medicines, books, or many of the things that you listed are all based on this versatile element, carbon. The amount of carbon present in the Earth's crust and in the atmosphere is quite meager. The Earth's crust has only 0.02% carbon in the form of minerals like carbonates, hydrogen carbonates, coal and petroleum, and the atmosphere has 0.003% of carbon dioxide. In spite of this small amount of carbon available in nature, the importance of carbon seems to be immense. Bonding in carbon. The covalent bond. Ionic compounds have high melting and boiling points and conduct electricity in solution or in the molten state. Melting and boiling points of some carbon compounds. Compound. Acetic acid. CH3COOH. Melting point 290 Kelvin. Boiling point 391 Kelvin. Compound chloroform. CHCl3. Melting point 209 Kelvin. Boiling point 334 Kelvin. Compound ethanol. CH3CH2OH. Melting point 156 Kelvin. Boiling point 351 Kelvin. Compound methane. CH4. Melting point 90 Kelvin. Boiling point 111 Kelvin. From the data on the boiling and melting points of the above compounds, we can conclude that the forces of attraction between these molecules are not very strong. Most carbon compounds are poor conductors of electricity. These compounds are largely non-conductors of electricity. We can conclude that the bonding in these compounds does not give rise to any ions. Let us now look at the electronic configuration of carbon. The atomic number of carbon is 6. The reactivity of elements is explained as their tendency to attain a completely filled outer shell, that is, attain noble gas configuration. Elements forming ionic compounds achieve this by either gaining or losing electrons from the outermost shell. In the case of carbon, it has 4 electrons in its outermost shell and needs to gain or lose 4 electrons to attain noble gas configuration. If it were to gain or lose electrons, first, it could gain 4 electrons forming C- anion. But it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is 4 extra electrons. Second, it could lose 4 electrons forming C4 plus cation, but it would require a large amount of energy to remove 4 electrons, leaving behind a carbon cation with 6 protons in its nucleus holding on to just 2 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon or with atoms of other elements. Not just carbon, but many other elements form molecules by sharing electrons in this manner. The shared electrons belong to the outer shells of both the atoms and lead to both atoms attaining the noble gas configuration. Before going to compounds of carbon, let us look at some simple molecules formed by the sharing of valence electrons. The simplest molecule formed in this manner is that of hydrogen. The atomic number of hydrogen is 1. Hence, hydrogen has 1 electron in its K shell and it requires 1 more electron to fill the K shell. So 2 hydrogen atoms share their electrons to form a molecule of hydrogen H2. This allows each hydrogen atom to attain the electronic configuration of the nearest noble gas, helium, which has 2 electrons in its K shell. The shared pair of electrons is said to constitute a single bond between the 2 hydrogen atoms. A single bond is also represented by a line between the 2 atoms. The atomic number of chlorine is 17. Chlorine forms a diatomic molecule Cl2. In the case of oxygen, we see the formation of a double bond between two oxygen atoms. This is because an atom of oxygen has 6 electrons in its L shell. The atomic number of oxygen is 8 and it requires 2 more electrons to complete its octet. So each atom of oxygen shares 2 electrons with another atom of oxygen. The 2 electrons contributed by each oxygen atom give rise to 2 shared pairs of electrons. This is said to constitute a double bond between the 2 atoms. Depict a molecule of water showing the nature of binding between one oxygen atom and 2 hydrogen atoms. The molecule has single bonds. Nitrogen has the atomic number 7. In order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons. This is said to constitute a triple bond between the 2 atoms. The electron dot structure of N2 and its triple bond can be depicted. A molecule of ammonia has the formula NH3. Draw the electron dot structure for this molecule showing all 4 atoms achieve noble gas configuration. Methane, which is a compound of carbon. Methane is widely used as a fuel and is a major component of biogas and compressed natural gas (CNG). It is also one of the simplest compounds formed by carbon. Methane has a formula CH4. Hydrogen, as you know, has a valency of 1. Carbon is tetravalent because it has 4 valence electrons. In order to achieve noble gas configuration, carbon shares these electrons with 4 atoms of hydrogen. Such bonds which are formed by the sharing of an electron pair between 2 atoms are known as covalent bonds. Covalently bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are small. This gives rise to the low melting and boiling points of these compounds. The electrons are shared between atoms and no charged particles are formed. Such covalent compounds are generally poor conductors of electricity. Allotropes of carbon. The element carbon occurs in different forms in nature with widely varying physical properties. Both diamond and graphite are formed by carbon atoms. The difference lies in the manner in which the carbon atoms are bonded to one another. In diamond, each carbon atom is bonded to 4 other carbon atoms, forming a rigid 3-dimensional structure. In graphite, each carbon atom is bonded to 3 other carbon atoms in the same plane, giving a hexagonal array. One of these bonds is a double bond. Graphite structure is formed by the hexagonal arrays being placed in layers one above the other. These 2 different structures result in diamond and graphite, having very different physical properties even though their chemical properties are the same. Diamond is the hardest substance known, while graphite is smooth and slippery. Graphite is also a very good conductor of electricity. Diamonds can be synthesized by subjecting pure carbon to very high pressure and temperature. These synthetic diamonds are small but are otherwise indistinguishable from natural diamonds. Fullerenes form another class of carbon allotropes. The first one to be identified was C60, which has carbon atoms arranged in a shape of a football. This looked like a geodesic dome designed by the US architect Buckminster Fuller. The molecule was named fullerene. Versatile nature of carbon. The formation of covalent bonds by the sharing of electrons in various elements and compounds. The nature of the covalent bond enables carbon to form a large number of compounds. 2 factors noticed in the case of carbon are: first, carbon has the unique ability to form bonds with other atoms of carbon, giving rise to large molecules. This property is called catenation. These compounds may have long chains of carbon, branched chains of carbon, or even carbon atoms arranged in rings. Carbon atoms may be linked by single, double, or triple bonds. Compounds of carbon which are linked by only single bonds between the carbon atoms are called saturated compounds. Compounds of carbon having double or triple bonds between their carbon atoms are called unsaturated compounds. No other element exhibits the property of catenation to the extent seen in carbon atoms. Silicon forms compounds with hydrogen which have chains of up to 7 or 8 atoms, but these compounds are very reactive. The carbon-carbon bond is very strong and hence stable. This gives us the large number of compounds with many carbon atoms linked to each other. Second, since carbon has a valency of 4, it is capable of bonding with 4 other atoms of carbon or atoms of some other monovalent element. Compounds of carbon are formed with oxygen, hydrogen, nitrogen, sulfur, chlorine, and many other elements, giving rise to compounds with specific properties which depend on the elements other than carbon present in the molecule. Again, the bonds that carbon forms with most other elements are very strong, making these compounds exceptionally stable. One reason for the formation of strong bonds by carbon is its small size. This enables the nucleus to hold on to the shared pairs of electrons strongly. The bonds formed by elements having larger atoms are much weaker. Saturated and unsaturated carbon compounds. Another compound formed between carbon and hydrogen is ethane with a formula of C2H6. In order to arrive at the structure of simple carbon compounds, the first step is to link the carbon atoms together with a single bond and then use the hydrogen atoms to satisfy the remaining valencies of carbon. For example, the structure of ethane is arrived in the following steps. Carbon atoms linked together with a single bond. 3 valencies of each carbon atom remain unsatisfied, so each is bonded to 3 hydrogen atoms, giving each carbon atom bonded to 3 hydrogen atoms. Draw the structure of propane, which has the molecular formula C3H8. You will see that the valencies of all the atoms are satisfied by single bonds between them. Such carbon compounds are called saturated compounds. These compounds are normally not very reactive. Another compound of carbon and hydrogen has the formula C2H4 and is called ethene. This molecule be depicted. Each carbon atom gets 2 hydrogen atoms to give 1 valency per carbon atom remains unsatisfied. This can be satisfied only if there is a double bond between the 2 carbons, giving us the electron dot structure for ethene. Another compound of hydrogen and carbon has the formula C2H2 and is called ethine. Draw the electron dot structure for ethine. Triple bonds are necessary between the 2 carbon atoms in order to satisfy their valencies. Such compounds of carbon having double or triple bonds between the carbon atoms are known as unsaturated carbon compounds, and they are more reactive than the saturated carbon compounds. Chains, branches, and rings. Such chains of carbon atoms can contain 10 of carbon atoms. The names and structures of 6 of these are given. Formula and structures of saturated compounds of carbon and hydrogen. Number of carbon atoms 1. Name methane. Formula CH4. Structure. Number of carbon atoms 2. Name ethane. Formula C2H6. Structure. Number of carbon atoms 3. Name propane. Formula C3H8. Structure. Number of carbon atoms 4. Name butane. Formula C4H10. Structure. Number of carbon atoms 5. Name pentane. Formula C5H12. Structure. Number of carbon atoms 6. Name hexane. Formula C6H14. Structure. We make the carbon skeleton with 4 carbon atoms. We see that 2 different skeletons are possible. Filling the remaining valencies with hydrogen gives us complete molecules for 2 structures with formula C4H10. We see that both these structures have the same formula C4H10. Such compounds with identical molecular formula but different structures are called structural isomers. Cyclohexane formula C6H12 to straight and branched carbon atoms. Some compounds have carbon atoms arranged in the form of a ring. The following structure: straight chain, branched chain, and cyclic carbon compounds all may be saturated or unsaturated. For example, benzene C6H6 has the following structure. All these carbon compounds which contain just carbon and hydrogen are called hydrocarbons. Among these, the saturated hydrocarbons are called alkanes. The unsaturated hydrocarbons which contain one or more double bonds are called alkenes. Those containing one or more triple bonds are called alkynes. Carbon seems to be a very friendly element. We have been looking at compounds of carbon and hydrogen, but carbon also forms bonds with other elements such as halogens, oxygen, nitrogen, and sulfur. In a hydrocarbon chain, one or more hydrogens can be replaced by these elements such that the valency of carbon remains satisfied. In such compounds, the element replacing hydrogen is referred to as a heteroatom. These heteroatoms confer specific properties to the compound regardless of the length and nature of the carbon chain and hence are called functional groups. Some important functional groups: heteroatom ClBr, functional group halo, chlorobromo. Formula of functional group ClBr substitutes for hydrogen atom. Heteroatom oxygen. Functional group: first, alcohol. Formula of functional group OH. Second, aldehyde. Formula of functional group CHO. Third, ketone. Formula of functional group CO. Fourth, carboxylic acid. Formula of functional group COOH. Free valency or valencies of the group are shown by the single line. The functional group is attached to the carbon chain through this valency by replacing one hydrogen atom or atoms. Homologous series. Such a series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called a homologous series. Carbon atoms can be linked together to form chains of varying lengths. In addition, hydrogen atom or atoms on these carbon chains can be replaced by any of the functional groups that we saw above. The presence of a functional group such as alcohol dictates the properties of the carbon compound regardless of the length of the carbon chain. For example, the chemical properties of CH3OH methanol, C2H5OH ethanol, C3H7OH propanol and C4H9OH butanol are all very similar. Successive compounds CH4 and C2H6, C2H6 and C3H8 differ by CH2 unit. The general formula for alkenes can be written as CnH2n, where n equals to 2, 3, 4. As the molecular mass increases in any homologous series, a gradation in physical properties is seen. The melting points and boiling points increase with increasing molecular mass. Other physical properties such as solubility in a particular solvent also show a similar gradation. But the chemical properties, which are determined solely by the functional group, remain similar in a homologous series. Nomenclature of carbon compounds. First, identify the number of carbon atoms in the compound. A compound having 3 carbon atoms would have the name propane. Second, In case a functional group is present, it is indicated in the name of the compound with either a prefix or a suffix. Third, if the name of the functional group is to be given as a suffix, the name of the carbon chain is modified by deleting the final E and adding the approximate suffix. For example, a 3-carbon chain with a ketone group would be named in the following manner. Propane minus E equals to propan plus 1 equals to propanone. Fourth, if the carbon chain is unsaturated, then the final ane in the name of the carbon chain is substituted by ene or ine. For example, a 3-carbon chain with a double bond would be called propene, and if it has triple bond, it would be called propyne. Nomenclature of functional groups. Functional group, halogen. Prefix chloro, bromo, etc. Example, chloropropane, bromopropane. Functional group, alcohol. Suffix, -ol. Example, propanol. Functional group, aldehyde. Suffix, -al. Example, propanol. Functional group, ketone. Suffix, -on. Example, propanone. Functional group, carboxylic acid. Suffix, oic acid. Example, propanoic acid. Functional group, double bond alkenes. Suffix, -ene. Example, propene. Functional group, triple bond alkynes. Suffix, -ine. Example, propyne. Chemical properties of carbon compounds. Most of the fuels we use are either carbon or its compounds. Combustion. Carbon in all its allotropic forms burns in oxygen to give carbon dioxide along with the release of heat and light. Most carbon compounds also release a large amount of heat and light on burning. These are the oxidation reactions. First, C plus O2 gives CO2 plus heat and light. Second, CH4 plus O2 gives CO2 plus H2O plus heat and light. Third, CH3CH2OH plus O2 gives CO2 plus H2O plus heat and light. Activity. Take some carbon compounds, naphthalene, camphor, alcohol, one by one on a spatula and burn them. Observe the nature of the flame and note whether smoke is produced. Place a metal plate above the flame. When burning naphthalene and camphor, it gives a yellow flame with very black smoke. When alcohol is ignited, it is ignited by a pure brown flame. A metal plate is placed on the flame of these unsaturated hydrocarbons compounds and a sooty is deposited on it. Saturated hydrocarbons will generally give a clean flame while unsaturated hydrocarbons compounds will give a yellow flame with lots of black smoke. This results in a sooty deposit on the metal plate. Limiting the supply of air results in incomplete combustion of even saturated hydrocarbons, giving a sooty flame. The gas or kerosene stove used at home has inlets for air so that a sufficiently oxygen-rich mixture is burnt to give a clean blue flame. If you observe the bottoms of cooking vessels getting blackened, it means that the air holes are blocked and fuel is getting wasted. Fuels such as coal and petroleum have some amount of nitrogen and sulfur in them. Their combustion results in the formation of oxides of sulfur and nitrogen, which are major pollutants in the environment. Oxidation. Activity. Take about 3 ml of ethanol in a test tube and warm it gently in a water bath. Add a 5% solution of alkaline potassium permanganate drop by drop to this solution. Potassium permanganate persists when it is added initially, the color is removed. Adding more KMNO4 leaves the extra KMNO4 unused in the process. So the color of KMNO4 does not fade. Carbon compounds can be easily oxidized on combustion. In addition to this complete oxidation, we have reactions in which alcohols are converted to carboxylic acids. CH3CH2OH, alkaline KMNO4 or acidic K2Cr2O7 plus heat gives CH3COOH. Some substances are capable of adding oxygen to others. These substances are known as oxidizing agents. Alkaline potassium permanganate or acidified potassium dichromate are oxidizing alcohols to acids, that is, adding oxygen to the starting material. Hence, they are known as oxidizing agents. Addition reaction. Unsaturated hydrocarbons add hydrogen in the presence of catalysts, palladium or nickel, to give saturated hydrocarbons. Catalysts are substances that cause a reaction to occur or proceed at a different rate without the reaction itself being affected. This reaction is commonly used in the hydrogenation of vegetable oils using a nickel catalyst. Vegetable oils generally have long unsaturated carbon chains, while animal fats have saturated carbon chains. Some vegetable oils are healthy. Animal fats generally contain saturated fatty acids, which are said to be harmful for health. Oils containing unsaturated fatty acids should be chosen for cooking. Substitution reaction. Saturated hydrocarbons are fairly unreactive and are inert in the presence of most reagents. However, in the presence of sunlight, chlorine is added to hydrocarbons in a very fast reaction. Chlorine can replace the hydrogen atoms one by one. It is called a substitution reaction because one type of atom or a group of atoms takes the place of another. A number of products are usually formed with the higher homologous of alkanes. CH4 plus Cl2 gives CH3Cl plus HCl in the presence of sunlight. Some important carbon compounds, ethanol and ethanoic acid. Many carbon compounds are invaluable to us. Commercially important compounds, ethanol and ethanoic acid. Properties of ethanol. Ethanol is a liquid at room temperature. Its compound formula is CH3CH2OH. Ethanol melting point is 156 Kelvin and boiling point is 351 Kelvin. Ethanol is a commonly called alcohol and is the active ingredient of all alcoholic drinks. In addition, because it is a good solvent, it is also used in medicines such as tincture iodine, cough syrups, and many tonics. Ethanol is also soluble in water in all proportions. Consumption of small quantities of dilute ethanol causes drunkenness. Even though this practice is condemned, intake of even a small quantity of pure ethanol, called absolute alcohol, can be lethal. Also, long-term consumption of alcohol leads to many health problems. Reactions of ethanol. First, reaction with sodium. 2Na plus 2CH3CH2OH gives 2CH3CH2O minus Na plus. Sodium ethoxide plus H2. Alcohols react with sodium, leading to the evolution of hydrogen. With ethanol, the other product is sodium ethoxide. Second, reaction to give unsaturated hydrocarbon. Heating ethanol at 443 Kelvin with excess concentrated sulfuric acid results in the dehydration of ethanol to give ethene. The concentrated sulfuric acid can be regarded as a dehydrating agent which removes water from ethanol. Properties of ethanoic acid. Ethanoic acid is commonly called acetic acid and belongs to a group of acids called carboxylic acids. 5 to 8% solution of acetic acid in water is called vinegar and is used widely as a precipitative in pickles. The melting point of pure ethanoic acid is 290 Kelvin and hence it often freezes during winter in cold climates. This gave rise to its name glacial acetic acid. The group of organic compounds called carboxylic acids are obviously characterized by a special acidity. However, unlike mineral acids like HCl, which are completely ionized, carboxylic acids are weak acids. Activity: take 1 ml ethanol, absolute alcohol, and 1 ml glacial acetic acid along with a few drops of concentrated sulfuric acid in a test tube. Warm in a water bath for at least 5 minutes. Pour into a beaker containing 20 to 50 ml of water and smell the resulting mixture. Sweet-smelling substance ester is present. These are used in making perfumes and as flavoring agents. Reactions of ethanoic acid. Esterification reaction. Esters are most commonly formed by reaction of an acid and an alcohol. Ethanoic acid reacts with absolute ethanol in the presence of an acid catalyst to give an ester. Esters react with sodium hydroxide to give back the alcohol and carboxylic acid. This reaction is known as saponification because it is used in the preparation of soap. Reaction with a base. Like mineral acids, ethanoic acid reacts with a base such as sodium hydroxide to give a salt, sodium ethanoate or commonly called sodium acetate, and water. How does ethanoic acid react with carbonates and hydrogen carbonates? Let us perform an activity. Take a spatula full of sodium carbonate in a test tube and add 2 ml of dilute ethanoic acid. Adding both gives rise to a gas. Pass the gas produced through freshly prepared lime water. What do you observe? CO2 gas produced by the reaction between ethanoic acid and sodium carbonate be identified by this test. Reaction with carbonates and hydrogen carbonates. Ethanoic acid reacts with carbonates and hydrogen carbonates to give rise to a salt, carbon dioxide and water. The salt produced is commonly called sodium acetate. Soaps and detergents. Activity: take about 10 ml of water in each 2 test tubes. Add a drop of oil, cooking oil, to both the test tubes and label them as A and B. To test tube B, add a few drops of soap solution. Now shake both the test tubes vigorously for the same period of time. You will see the oil and water layers separately in test tubes A immediately after you stop shaking them. Leave the test tubes undisturbed for some time and observe. The oil layers separate out. In test tube A, this happens because oil does not dissolve in water. This activity demonstrates the effect of soap in cleaning. Most dirt is oily in nature and, as you know, oil does not dissolve in water. The molecules of soap are sodium or potassium salts of long-chain carboxylic acids. The ionic end of soap dissolves in water while the carbon chain dissolves in oil. The soap molecules thus form structures called micelles, where one end of the molecules is towards the oil droplet while the ionic end faces outside. This forms an emulsion in water. The soap micelle thus helps in dissolving the dirt in water and we can wash our clothes clean. Activity: take about 10 ml of distilled water or rainwater and 10 ml of hard water from a tube well or hand pump in separate test tubes. Add a couple of drops of soap solution to both. Shake the test tubes vigorously for an equal period of time and observe the amount of foam formed. Both test tube gets more foam. We find foam in the test tube of distilled water. In a hard water test tube, white curd-like precipitate is formed. Activity: take 2 test tubes with about 10 ml of hard water in each. Add 5 drops of soap solution to one and 5 drops of detergent solution to the other. Shake both test tubes for the same period. First test tube have the same amount of foam. Detergent test tube is a curdy solid formed because detergent has an effective effect in hard water. While bathing, that foam is formed with difficulty and an insoluble substance remains after washing with water. This is caused by the reaction of soap with the calcium and magnesium salts, which cause the hardness of water. Hence, you need to use a larger amount of soap. Another class of compounds called detergents as cleaning agents. Detergents are generally ammonium or sulfonate salts of long-chain carboxylic acids. The charged ends of these compounds do not form insoluble precipitates with the calcium and magnesium ions in hard water. Thus, they remain effective in hard water. Detergents are usually used to make shampoos and products for cleaning clothes.